Thank you again for joining me for another video. This time it's the sixth one on Chapter 2, Year 13, Edexcel A-Level Maths, Functions. So this time what we're going to be having a look at is transformations of functions, which links to what we've seen in previous year 12 work, but we're just going to take it a slight step further. Now again, we know about the modulus, we can also apply what we know about that function to graphical transformations, but it's all going to be recapped and extended here and explained. But before doing so, let's get warmed up with some warm-up questions. Here they are, 4 to attempt. My suggestion would be to pause the video now and try these on your own, and when you're ready to see the solutions, press play, and hopefully mine will be the same as yours. So assuming you've done that, let's have a look together at warm-up question 1. So first of all, we have to express 2 over 4y squared as partial fractions. So the key spot here is 4 minus y squared is a difference of 2 squares. So what we can say here, first of all, is that 2 over 4y squared, sorry, 4 minus y squared, is of course the same as 2 over 2 plus y, 2 minus y. And then we can set this as 2 separate fractions with numerators a and b, and then try and find what a and b would have to be. So we can say this is going to be equal to some unknown numerator a, all over 1 factor, 2 plus y, plus some b, we don't yet know, all over 2 minus y. So if I just take this part here and multiply everything by 2 plus y, 2 minus y, then what we'll hopefully see is, if we were to do that, on the numerator, if we multiply everything by 2 plus y, 2 minus y, that will cancel. So then we'll just have 2 over here will equal a. But then if we're multiplying everything by 2 plus y, 2 minus y, oops, just change colour here, then the 2 plus y root will cancel the 2 plus y we're multiplying by, but the 2 minus y will remain. And in a similar fashion for b, we'll then have plus b. If we multiply this one by 2 plus y, 2 minus y, the 2 minus y will cancel, and we're left with 2 plus y there. We can now equate coefficients or simply sub in useful values. So first of all, I would suggest just trying y equals 2. Let y equal 2. We can get 2 equals, the a term will cancel because 2 minus 2 is 0. We then have b multiplied by 4. So 2 equals 4 lots of b. Therefore, dividing by 4, b must be a half. In the same way, if we were now to let y equal negative 2, so we can cancel out the b term and focus on what the a is, then we get 2 equals a, brackets 2 minus minus 2, which means a multiplied by 4. So 2 equals 4a. And of course 2 plus minus 2 cancels, like I said. So again, dividing by 4, we see that a as well is equal to a half. So therefore, answering the question as we were asked, so 2 over 4y, 4 minus y squared, equals a, which is a half all over 2 plus y. But because it's unusual and probably not simplistic enough to have a fraction within a fraction, I'm going to write it as 1 over 2 lots of 2 plus y, and then plus 1 lot, and 2 minus y. So essentially, a is the half here, and b makes this half here. So let's have a look at the second warm-up example, warm-up question 2. So here we have to write the first 3 terms in ascending powers of x of the binomial expansion 3 plus 2x all to the power 7, giving each term in its simplest form. What I'm going to do first of all is to remind you of what you'll be giving in the formula book anyway, which is the general binomial expansion for whole number natural powers. So we'll be given this in the formula book, so we can now apply it with our a being 3 and the b being 2x. So essentially we can just think about the a as being 3 and b being 2x. And for completion, I suppose you could say the n here is clearly 7. So therefore, using this, 3 plus 2x to the 7 will expand to 3 to the power 7 and the power of the first thing will reduce by 1 each time, as the power of the second thing increases by 1 each time. So now we had 2x to the 0 first of all, which is 1, so we didn't need to include it. But now we're going to have 2x to the positive 1, and now we're going to have n choose 1, which we write as 7 choose 1. Go again, drop the power 6 to a power 5, increase the power 1 of 2x to a power 2, and now we have 7 choose 2. And this will keep going and going and going until eventually we got to 2x to the power 7. However, all this question's asking us is the first 3 terms. So we're just wanting to simplify these 3 bits here, 1, 2, and 3. So on calculators, we can do 3 to the power 7. Like that gives us here. 3 to the power 7 is going to be 2187. So the constant term is 2187. Then we're going to add on 3 to the power 6. So 3 to the power 6. The numerical term will just be times 2 to the 1, which is just times 2. Then multiplied by 7, C1, which gives us 10,206. So the x term is 10,206. And finally, we want the 3 to the power 5 now. So just alter that 6 to a 5. And that 2, we now want to square. So I can either type in 2 squared or just type in 4, because that is 2 squared. And 7 choose 2. So alter that 1 to a 2, press equals. And you can see here we get 20,412. So the x squared term is 20,412. Also, it goes on because we only want the first 3 terms, we can curtail it to that. And then we're done. So we can move on to try question 3. Question 3, we have points A and B with coordinates 5, -1 and 13, 11 respectively. We're told first of all to find the coordinates of the midpoint of A, B. So let's first of all do that. So what we're told here is A is 5 -1, B is 13, 11. So I'd suggest to sketch these on a piece of paper or on your jotter pad, whatever you've got. So roughly, in relation to each other, put 5 -1 first. 13 will obviously be to the right, and because 11 is bigger than -1, it'll also be higher. So put 5 -1, then a bit to the right and a bit up, 13 and 11. Now the midpoint of A and B is found by averaging the x-coordinates of these 2 points together. That'll be the x-coordinate of the midpoint, and then we average the y-coordinates too. So 5 add 13 is 18, half of that will be 9. 11 add -1 is 10, half of that is 5. So the midpoint will be 9, 5. So the midpoint, which I'm going to add in green, will simply be the point 9, 5. Next, we're told that AB is the diameter of the circle, so we need to find an equation for C. So because AB is a diameter, we can then picture the circle overlaid on top, and to work out the equation for C, a necessary component is to work out the radius of this circle squared. Now I can do this because I know the centre's 9, 5, and this point here, for example, is 13, 11. From the green to the red point is the radius, so I can construct a right-angled triangle on this to then calculate what R would be. So from 9 to 13 we're going 4 along, and from 5 up to 11 is 6 up. So then using Pythagoras I can calculate R. But in fact we don't even need R, we just need R squared. So for part A, just to answer it like we've been asked, it's actually 9, 5. I'll put it on the diagram but I've not put it here, so we can do that now. And the equation for C, the general form of an equation of a circle with a centre A, so let's say centre circle, making a meal of this. So let's say equation of a circle, just to remind us, equation of a circle with a centre A and B. Hopefully you remember from year 12, but if not, it's x minus a all squared plus y take b all squared equals r squared. So using Pythagoras, I can work out what r squared is. R squared is going to be 4 squared plus 6 squared. In other words, r squared is 16 plus 36, which is 52. So I can say that r squared is definitely 52. We also know that the a coordinate, so the x coordinate at the centre, is 9. And so I know here that a is essentially 9. And in addition to that, I can also say that b, the y coordinate at the centre, is 5. So filling these in, inputting a for 9, subbing 5 for b, and subbing 52 for r squared, the equation of this particular circle is x minus 9 squared plus y minus 5 squared equals 52. Because it's at the centre, 9 and 5. So the coordinates of the centre, we just switch the signs. So 9 becomes minus 9 over bracket, 5 becomes minus 5. And that's r squared, which is 52. Final warm-up question. Find the value of x for which log base 2 of 2x minus 1 minus log base 2 of x equals negative 2. So this side is in terms of log base 2, this bit isn't. So I need to just think about how I can rewrite minus 2 in terms of log base 2. Now, how the base relates to what the value we're taking the log of and that particular value can be quite easy to forget. I would always remember it in terms of log base 10, personally. So log base 10 of 100, I always just used to recall that's 2, because 10 squared is 100. In other words, the 100 we get from taking the base to the power of the particular answer. In other words, 10 squared gives us that. 10 to the power of 2 is 100. So let's think about how we can do the same here. What we're wanting is log base 2. So we want log base 2 of some value, let's call big X. We want that to be equal to minus 2. So as we just showed over here, the 100 was 10 to the power of 2, and the same way this big X must be 2 to the power of minus 2. So in other words, big X is going to equal 2 to the power minus 2. So we can rewrite this now as log base 2 2x minus 1 minus log base 2 of just x equals log base 2 of 2 to the minus 2. Now 2 to the minus 2 equals a quarter. So we can change this to log base 2 of a quarter like so. So I just wrote minus 2 in this form here. And if you want to, just double check with your calculator if you're not entirely sure. That's a fairly wise strategy. So if I do the log button, change it to base 2, and type in 1 quarter, we have minus 2 as we needed. Now, using the laws of logs, I have log of something minus log of something else, and both are to the same base. So I can combine these things into a single fraction. So I can say it's the same as log base 2 of 2x minus 1 all over x. And that equals, on the other side, log base 2 of a quarter. So we have an equation. One side is equal to the other. Both are being logged to the same base. And so if one's equal to the other, that can only be so if this value is equal to a quarter. So from this, we need to deduce that the equation we're needing to solve is 2x minus 1 all over x set to be a quarter. Now you can solve this whatever way you want as long as it works. I tend to do it in terms of cross multiplication. So 4 times 2x minus 1 will equal x multiplied by 1. In other words, x equals 4 lots of 2x minus 1. I expand out, I get 8x minus 4. Subtract x from both sides. Add 4 to both sides. and divide by 7. So therefore x must be 4/7 in exact form. Let's now have a look at the main part of the lesson, graphical transformations. So, what if we were to combine two or more transformations and the order were crucial? So before we've translated a function or stretched a curve, for example, but how do we combine a complicated mixture where we've got two or more transformations to consider? So unfortunately, the order transformations are performed on a function, it does actually matter. So we saw that in section 2.1 with a modulus. To generalize it further, if we want to sketch a complicated function, we need to decide on the basic parent function from which it is built upon, for lack of a better word. So in other words, we need to decide on a suitable parent function, call it f of x, and then build it up to the required form af brackets bx plus c plus d, where a, b, c and d represent parameters that have transformed from f of x to something slightly different. A and b need to be non-zero, otherwise there would be a non-function. If a was 0, it wouldn't be a function, and if b was 0, it wouldn't be a function of x. So we go from f of x to this complicated form by applying the following order of transformations and their resultant effects. So this is where the order is absolutely crucial. So what do we deal with first? A, B, C, or D? Well, let's have a look. Pardon me. First of all, we do C, horizontal translations. Now, because this is inside the brackets, it works opposite towards common sense. It looks like we're adding C to the x values, whereas actually we're going to minus C from the x values. If it's inside the function bracket, it affects x in an opposite to common sense way. After doing the horizontal translations, the next thing we need to do is a horizontal stretches, which relates to b. Again, it's inside the function bracket. Common sense would seem to say x is being multiplied by b. Opposite to common sense, therefore, what's actually happening is the x coordinates are being divided by b. So just like BIDMAS, if you notice here, we've worked out the bracket bit first. But in terms of BIDMAS, we'd normally multiply before adding. Here, we've done the adding part before the multiplying. So again, it's an extension of the inside the function brackets. It works as opposite. Then we move outside of the brackets. We then do A. A is just multiplying f. It's outside the brackets, so it affects y in a common sense way. The a multiplies the y values by a. Then finally we do d, which is just a vertical translation where everything we just add d to it. So we just add d onto every single y value. As a little hint, which I've mentioned as well just before, the order of operations is the same as BIDMAS, but with the usual order inside the brackets also being reversed. So in other words, we subtract c before we divide by b. So you work from the inside out essentially. Remembering the golden rule, inside the brackets is opposite to common sense. Now, in mini tasks for you lot in either pairs or small groups, I'd like you to decide on a suitable parent function for the below functions. The first one's been done, so imagine you needed to sketch y equals 5 sine brackets 2x minus 10. That's horrible. You start from the more basic one, which should be f of x being sine x, and then build up from there. So assume you've had a try of these. This one here, the main thing that's happening, this is a mod function. So the parent function for this one would be f of x equals mod x. In function notation, the main thing that this one is a natural log type of function. So in parent node function, in f of x, this would be simply ln x. This one, the main sort of characteristic is it's a reciprocal function, and the main reciprocal function starts with being k over x. So the most obvious place to start here would just be to take y as 1 over simply just x, though we can translate from there. This one, you can be forgiven for not knowing where to begin with this one, because we've got an exponential and then the mod as well. So just remember what I said before, start from the inside and work out, essentially. So starting from the inside, we've got an exponential function, so we worry about that one first. So consider f of x to be e of x. Now some worked examples. So we've got a curve, y equals f of x, passing through a point P, which is minus 3, 2, on a coordinate grid. We need to find the coordinates that P is transformed to when the function f is subjected to the following transformations. So let's remind ourselves of the order of transformations first. So just from before in the notes, let's just pay attention to this. So first of all, we've got y equals 2f 0.5x. So here we've got a, which is 2, and b, which is 0.5. So start with p minus 3, 2 first of all. So the first thing, obviously, was no c to consider, so we look at b next. So we're going to divide the x values by b. So in this case, we're going to divide the minus 3 by 0.5. So divide x by 0.5. The minus 3 will become minus 6. Y value is not affected. Now, afterwards, we can deal with a. A multiplies the y values by itself. So we're going to take this y value and multiply by 2. Next. So 2 multiplied by 2 gives us 4. Therefore, the point minus 3, 2 finally lands up at the point minus 6, 4. For b, the main thing here is this negative 3. That negative 3 is just a number outside of the function brackets, so this works as our d. So let's consider this as f of x plus minus 3. Start from the inside and work out, so we can worry about the modulus signs after. First of all, just start with f of x plus 3. Plus minus 3, I mean to say. So this minus 3 will essentially just add minus 3, in other words, subtract 3 from the y values. So we start with minus 3, 2, then we're going to subtract 3 from y. So 2 add minus 3, in other words 2 take away 3, gives minus 1. So now we go to minus 3 minus 1. However, y isn't simply f of x minus 3. It's the modulus of all of that. So if we take the mod of a value, it must return a non-zero value. So what we do finally is we take the modulus of minus 1. So mod for y coordinate, x can be negative, but y, of course, is modded. So mod of minus 1 is 1, so this point ends up going to minus 3, 1. The last one, part C, we've got a b value which is 2, our c is 1, and d is minus 1. So first of all, we deal with c. So instead of adding 1, which is what you'd seem to do, inside the brackets, so opposite to common sense, we're going to subtract 1 from the x value first. So start with minus 3, 2, take away 1 from x, that's going to give us minus 4 over 2. So we've dealt with c, next is b. b is what we divide x by, so I'm going to divide the x values now by 2. So x is minus 4 divided by 2 is minus 2, so now we're at minus 2, 2. The final step is to deal with this minus 1. It's outside the brackets, so it affects y in a common sense y. We simply take 1 from the y values. So 2, take away 1, or add minus 1 if you want to be technical, we get minus 2, 1. So that's where minus 3, 2 ends up with if f of x transforms to this beast. Question 2, let's picture how a curve gets translated and looks under transformations. So we've got a diagram on the right showing a sketch of y equals fx. The curve passes through the origin, the point A, which at the moment is 2, 1, 2 minus 1 rather, and the point B, which is 6, 4. So sketching the spaces below these graphs. So y equals 2 f of x minus 1. So first of all, what's going to happen is we multiply the y values by 2. So a would go to 2 minus 2. Let's get the right colour first. Just multiplying that by 2 would get 2 minus 2. B would go to 6 and 8. The origin, that multiplied by 2 will stay as it is, but then what we're going to do is knock 1 off each of these y values. So essentially, that minus 2 will become minus 3. That 8 will become 7. and the y-axis intercept will be 1 lower, it'll be at -1. So this one here is going to be looking double as high, it's going to be going up faster because y values have doubled, but it's going to cross this origin, it's going to be 1 lower. So if I just cheat here and grab this, it's going to look slightly elongated like so, something like this, and then I can just add on the actual points. So this here is -1, A goes to 2 -3, and B becomes 6, 7. For B, y equals f brackets x plus 2, then plus 2. So what's going to happen here, that plus 2 is going to be -2 from the x values, and then plus 2 there means we're going to add 2 to y. So this curve here, it was like this, essentially going to go 1, 2, then 1, 2. So 2 minus 3, that's actually going to be at the point now, in fact if I just show you step by step, so essentially if I take 2 from x and add 2 to y, the point A will go to 0 and 1, so actually that should be about here, just so it fits on, thank you. B, if I take away 2 from x and then add 2 to y, B will become 4 and 6. Call that 1. And then we're done. Part C, y is a quarter f2x. Oops. So for this one, if I just clear away this, and then we can consider what we need for the new A and the new B. What we're going to do first is the 2x. So that 2 means we're going to divide the x values by 2. So A will become 1 minus 1 for the meantime. B, in the meantime, will become 3 and 4. And now we're going to quarter the y values. And so a quarter of -1, that's going to become -1 quarter. And 4 quartered just becomes 1. Now, this will still go through the origin, because 0 divided by 2 is 0, and a quarter of 0 is still 0. So essentially, it's going to be going up as only a quarter as fast, but it's going to be squished in by a factor of 2. So this one is going to be something like this. So it's going to be, the 2 minus 1 will happen quicker. It won't look as though it goes as high. So it's going to be a scaled down version of its former self. So it's going to cross at the origin. The point A will be at 1 minus a quarter. And point B, in other words B dashed, will have moved to the point 3, 1. Finally now, part D of this, y equals f of 3x minus 12. So again, all this is inside the brackets, inside think opposite, so I'm going to deal with this minus 12 first. So the first thing we're going to do is add 12 to the x values. So that would take A to be 14 minus 1. That would take our B all the way up to 18 and 4. Then, because it's a 3, we need to remember to then divide the x values by 3. And so this one now, for A, becomes 14 over 3, and for B, that becomes 18 over 3, which of course is just exactly 6. So B goes to 6, 4. And the origin, again, this one here, we add 12, and then 12 divided by 3 is 4. So the origin would move to the point 4, 0. Well, obviously the origin is the origin, but this point here, moves 4 to the right, essentially. So what that means now, we can sketch this on. So it's going to be something like this. Goes lower and higher, and then back down again. So A dashed, if you like, that's now going to be 14 thirds minus 1, and B will be the point 6 and 4. Worked example 3. This time f of x is defined as ln x, where x is greater than 0. First of all, we need to sketch a graph of y equals 2 fx minus 3, and then finally b, y equals the mod of f of minus x. On each diagram, we're going to need to show where the graph meets or crosses the x-axis, and in each case, state the equation of the asymptote. So first of all, let's just remind ourselves what the graph of ln of x looks like. So ln x, you need to recall, looks like this as its characteristic shape. So now, with this, it goes asymptotic at the y-axis, comes up through 1, and then looks like it trails off. It's not asymptotic, but the rate of increase does slow. This will eventually go towards infinity, but it tends to infinity slower and slower as x goes larger. So now we can think about 2f of x minus 3 and y equals mod of f minus x. So if we take y to be 2 lots of ln x, obviously y will be increasing twice as fast, which means at some point the red curve, because I'm going to sketch this one in red, this will overtake the y equals ln x curve. It'll start off lower because of this minus 3 part, but eventually, because y will be going up twice as fast, at some point it will overtake like this. And so the graph of y equals 2 f of x minus 3 looks a bit like this. Now in terms of where it crosses the x-axis, here I need to just set 2f of x minus 3, in other words 2 ln x minus 3, set it equal to 0. So then if I add 3 to both sides, 2 lots of ln x needs to equal 3, divide by 2, natural log of x needs to be 3 over 2. I can then exponentiate both sides, so e to the ln x will equal e to the 3 over 2. E and ln essentially cancel for lack of a nicer term. So in other words, the x-axis intercept is e to the power 3 over 2. So I can label this in like the question asked. And the asymptote is still the y-axis. So in other words, the asymptote is x equals 0. For b, y equals the mod of f of minus x. Well, the graph of f of minus x, we need to recall, is a reflection in the y-axis. So if I were to just do, first of all, the graph of f of minus x without being modded, I'd get this. And then, if I were to take the mod of that and make anything underneath the x-axis be reflected, what I'd then have is something like this. So if I just erase anything underneath the x-axis like so, and then reflect it upwards, like something like this, that should be going closer to the y-axis, not further away, but it's very hard to sketch when you're so close to a line. So essentially it looks something like this. Here, this would be minus 1, where it touches the x-axis, and again the asymptote would again be the y-axis, or essentially the line x equals 0. Now one final worked example 4. So To be fair, this one's going above and beyond. This one is a challenge, but just remember, let's start from the inside and work out. So, sketch this graph indicating any points of intersection with the coordinate axes, turning points, and any asymptotes. A challenge and a half. So, let's do it step by step. Let's start with a simpler looking function and build up to this. This is f of x, so let's introduce g of x as the parent function. Going back to the paired activity, once we introduced the idea of multiple transformations, this one was actually one of the student activities. The suggested parent function for this was e to the power x, so I'm suggesting we introduce g of x as e to the power x. We now need to sketch these graphs, so here are 5 pre-drawn graphs. So starting with the graph of e to the x first. So g of x is e to the x. So e to the x minus 1 would be obtained if we did g of x to the minus 1. G of x is e to that thing. So g of x minus 1 would translate to e to the x minus 1. So let's graph now g brackets x minus 1. So if it's g of x minus 1, that actually means we're going to add 1 to the x values. So let's think about what we have first of all before we do that. The exponential function is going to cross at 1. So if I think of g of x minus 1 next, down here, g of x minus 1 would be e to the x minus 1. So it's going to be a shift of positive 1 in the x direction. This point now will be at the point 1, 1. And that's going to be a height of 1. And this y-axis intercept, we just need to sub in when x is 0. When x is 0, the y-axis intercept will be e to the power 0 minus 1, which is just e to the minus 1. So now the y-axis intercept is e to the minus 1. Now I've got that step, I can then do g brackets x minus 1 minus 1 here. So if I do g x minus 1, then a minus 1 outside the brackets, the minus 1 on the outside will lower the curve by 1 unit everywhere. So next, let's consider g of x minus 1 minus 1, which is e to the x minus 1 minus 1. So all these points here are going to be lowered by 1. So this point here, 1, 1, will go to 1, 0. So it's going to be on the x-axis. And the y-axis intercept now will be e to the minus 1 minus 1. Like so. Now, all this here, we take the mod of all of that. So now consider the graph of the mod of all of this. So what would the modulus of g brackets x minus 1 minus 1 look like? In other words, the graph of the mod of e to the x minus 1 minus 1. Well, anywhere where the graph is non-negative will stay looking as it is. Anywhere underneath the x-axis, though, is reflected in the x-axis. So this bit underneath will go like this, and this curving bit here will stay the same. So the graph will look something like this next. That stays because it was already on the x-axis. The y-axis intercept is going to be multiplied by minus 1. So this thing here multiplied by minus 1 will be 1, then minus e to the minus 1. The final step, this 1 on the outside, working to the absolute outside now we've done the inside, this whole thing plus 1. So the final step, the whole thing plus 1 rather, that should be a plus, silly me. Like so, that's just going to shift the whole lot up 1 unit. So that's going to be again at 1, 1. This point here is going to be this plus 1, which will be 2 minus e to the minus 1. Like so. And the asymptote, this one here, e to the minus 1 is at a point there, and as x gets smaller and smaller and smaller, this here will approach a value of 0. The mod of minus 1, 0 minus 1 is 1, plus 1 is 2. So this will approach 2 from below. So the asymptote for this one is going to be at the line y equals 2. Like so. So this is our completed and final transformed function. This is now f of x, like so. So now we've had some warm-ups and examples showing you what to do. It's now for you to try some of these on your own independently. So in the book, page 47 to 48, you'll find a good selection of questions, but I'm just going to suggest you try 2, 3, 4, 5 and 6. Try them all, of course, if you can and you have time, but I think questions 2 to 6 are the key ones to give you a good flavour of what to do. So try them and seek help if you're stuck or unsure. And again, sincerely, thank you for tuning in and take care of yourselves until next time. From Mr. Bailey, goodbye for now.